Welcome to Unical Pre-Degree Digital Lecture Series. I am Ubon Camillus Ben, and I'll be presenting on magnetics and magnetism. Alright, so what are magnets? Recently, the power of magnetism has increased. The applicability of magnetism has increased even more with the search for cleaner and renewable sources of energy. Recently, researchers made a groundbreaking discovery. They were able to use magnetism to carry out fission. If you can remember, in our secondary schools, just one or so, we were told that fission is not possible. Fission is not possible. Of course, what's fission? Fission is basically when you join two nucleus together, and it can only happen in the sun because of the amount of energy needed, and of course the heat that will be released, to melt whatever container you want to use in keeping or storing the energy. So, or probably any container that we use when trying to create the energy. So recently, they used magnetism. They were able to put this fissionable nucleus in a magnetic field, and it was a groundbreaking discovery. You can just Google that, you see it. I'm trying to tell you how powerful magnetism has become. Right. So, what are magnets? Magnets are basically materials that attract other metals. There are three classes of magnets. We have the natural magnets, we have the artificial magnets, and of course the electromagnets. The natural magnets are the ones in rocks, the ones that comes in nature. They are rocks that are naturally magnetic in nature. They mostly used in hydrocarbon exploration. A very good example of that is the magnetites. The magnetites, which is a very popular geologic material. The magnetites. You also have the artificial magnets, which are the ones you see around, the ones that are created artificially using different methods that will show to you in this lecture series. Of course, we also have the electromagnets, which is created using the laws of electromagnetism. Of course, passing current electricity through a conducting material. Alright, we can also categorize magnets into permanent and temporary. Permanent magnets are magnets that retain their magnetic property for a very long time. All natural magnets are conventional permanent magnets. We also have temporary magnets that only have short-term magnetism. And magnetism does not last for long. So, of course, magnets are critical to electric systems, mostly used for generating energy in your transformers. That iron there that you see is basically a magnet. And also for the operation of motors. Of course, your coils. Once you see a coil there, just know that what they want to create is a magnet. Of course, almost all things have coils. Your mowers, your cars, your fans. Almost all equipments have motors, so you can imagine how important magnetism is to the world today. Of course, also operation of relays. Magnetism is also very important operation of relays. Now, there are basically two types of material that we commonly use in making magnets. We have the iron and the steel. These are all magnetic conductors, right? They are all conductors and materials that are commonly used in making magnets. Alright, so what's the difference between two of them and what guides the choice of each of these materials? For iron, For iron gets magnetized faster. So if you want a material that you want a magnet, you understand, the magnet that you want to create in a short period of time, for short-term use, right? And you need a quick magnet, something that something can easily magnetize easily. You go for soft iron. It has susceptibility, high susceptibility. That means it can easily be magnetized. However, it has low retentibility. That means it loses its magnetism as soon as the inducing magnet is removed. Hence, soft iron is said to, of course, have high susceptibility and low retentibility. This property of soft iron allows it to be useful for making temporary electromagnets, where we need a strong, right? We need a strong but temporary magnet. Now, the core of a transformer, for example, is made up of soft iron. Now, steel, on the other hand, is slow to be magnetized. Take a very long time to magnetize steel. However, it retains the acquired magnetism for a very long time. Steel has low susceptibility but high retentibility. Steel are mostly used for making permanent and horseshoe magnets. Alright, now there are several methods of magnetization. You may ask yourself, this is a conventional iron. We have iron everywhere. We have steel everywhere. Of course, we have iron rods. We have steel plates and steel spoons. They are not magnets. So how do I create magnets from these conventional and harmless materials? There are several ways of creating magnets, but I'm going to discuss the most popular ones, about 4 of them. Just going to look at the 4 most popular methods of magnetism. Okay, so let's go for the first one. Let's see. We have the single touch method. So what's it about the single touch method? Here, first of all, you keep your iron on a wooden table. Of course, the wooden table is a non-conductor. So place your iron rod, as you can see in the picture here, on the top left hand of your screen. You put the bar to magnetize on a wooden table in a strong permanent magnet, right? And one of its poles, right, is kept at one end of the rod. You can see in this our case here is a north pole that is kept at one end of the rod. Originally, that north south on the rod will not be there. We will not know which one is the north and which one is the south. So that's just a harmless rod. So what you do is you gently rub the rod, that one end of the rod, from one end. You gently rub the magnet, right? That one end of that magnet, you gently rub it from one end of the rod to the other end of the rod. When the other end is reached, that's when you get to the left. Let's assume you can see the direction there. Let's say you get to the right, yes, the right end. What you do is that the magnet is lifted and the process is repeated. Starts from here. You place it at contact, you drag it, it gets to the end, you lift it and start again. You do this repeatedly. At a point, the rod will get magnetized, and it will magnetize such that the starting end, which you have here, right, will act as a north pole, while the other end will become the south pole. We also have another method, which is the divided touch method. Here, what do you do? In this case, you keep the rod on top of, you can see 2 bar magnets there, right? You can see 2 bar magnets there. Those 2 bar magnets are kept on the table, and the rod is now placed on the bar magnets, right, with opposite poles facing each other. Here you can see south is at the one end, while north is at the other end. So you now what you now do is that you take 2 strong permanent magnets and bring 2 opposite poles, right, to touch at the middle. You can see here we have south and then we have north. We have south and we have north. Gently rub the two magnets on a rod and move away from each other towards the end. You put it there, as you can see on the board, and you move slowly away from the middle. Once you get to the end, you take it up and then come back to the middle again and repeat the same step. You keep repeating this separately until finally the rod is magnetized. Now in this case, the rod will magnetize such that the end where the south pole leaves the rod, right? The end where the south pole leaves the rod, right, becomes the north pole, and the end where the north pole leaves the rod becomes what? The south pole. In this case, you can see that the south is going to the left. So where it gets to the end, that will now become a north pole. Where you have end, you can see end there. And the other rod, which we touched with the north pole, you take it towards the right. And when you reach the end, that side will now be the south. It will now be the south pole. Alright, another very popular one is a double touch method, which I love so much. It's very similar to the divided touch method, only that you don't move them differently. What you have, you also need two permanent magnets, right, of different polarities. However, in this case, you don't bring them together. What you do is that you put a cork or a piece of wood. The two magnets will be held together with a piece of wood or cork, such that the opposite poles are together. Now this combination is now placed on a rod at the center and then move to and fro without lifting it. You can see this is different. Others, when it's going to the end, you lift it and come back again. But in this case, you move it to and fro without lifting it. Now the rod gets magnetized such that the opposite pole that is to the nearest strong magnet is created at its end. You can see here was south, right? South. On the south, when the south is closer to the left end, right, and that becomes the north pole, right? The north is closer to the right end, and after being magnetized, it becomes the south pole of the new magnet. Finally, we have the electrical method, which is the most popular way of getting material magnetized. How does this work? It's very easy. In fact, commercially, the electrical method is used in making magnets. That's because you simply have to wrap a coil of insulated material around the rod and then connect it to electricity. You can then go and sleep in time it will be magnetized. Alright, so here you wound the insulated copper wire around the rod, forming a coil, just the way you see it here on your bottom right hand side of your screen. Now the rod gets magnetized over time. Such magnets are usually called electromagnets. The end of the rod at which current enters, you can see the left hand side of your rod. That side where current enters, right, in an anti-clockwise direction becomes the north pole, while the other end becomes the south pole. Alright, please, I hope you understand. If you don't, please can ask your question in the interactive forum. Alright, so now what about the magnetization? Of course, we may be tired of the magnet. We just want to break it. Whatever has a beginning will definitely have an end. We do not want our magnet again. Of course, we just want to get our iron back. So situations like that, we want to tear it, scatter it. How do we go about with that? There are several methods of the magnetization, and I'm going to give you very few of them. However, there are so many of them. First of all is rough handling. Just rough handle your magnet over a long time. It's going to lose magnetism. Remember that was induced just the way you paint. If you paint your house, right, and it keeps raining, the roof does not protect the paint over time, it's going to be worn. The paint is going to leave. What about your shoes? You keep rough handling the shoes. Over time, the shoes will be worn. It just works the same way. Magnetism works the same way. You keep rough handling your magnet. Over time, it loses magnetism. We also have another one: continuously dropping the magnets from a height, right? Or consistent hammering. You hammer it consistently. So, alright, so in this case, you simply go up, drop it, go back, pick it, drop it, go back, pick it, drop it. Or you just get a hammer and keep hitting it. Keep hitting it. Over time, the material will lose all its magnetism. Right. Another very popular way is heating the magnet to a very high temperature. Once you heat that magnet to a very high temperature and maintain that high temperature for a long time, of course, you know that temperature agitates electrons. Over time, the configurations will change, right? The configurations of those electrons will change, thereby losing the magnetism. All right. We also have another method which is also popular. Remember that we created magnets by passing electric currents, right, through the coil. We can also pass high frequency alternating electric current through the rod, right? And by doing this, the material can also lose its magnetism. Very important to time. Just allow your magnet to wallow over a long time. Of course, over time, with time, it keeps losing its magnetism gradually until it's lost all its magnetism. Finally, keeping two magnets of similar strength with their like poles facing each other, probably a south pole facing the south pole. Of course, you know that this is going to repel, right? You know that this is going to repel. So you just keep them together. Over time, if you cannot push the other magnet away, it will boomerang, and come back on itself, right? Fighting its own magnetism, and over a long time lose the magnetism. All right. So those are the methods of demagnetization. Please, I hope you understand. Just like I usually say, if you don't, please use the interactive forum. Alright, so we're going to look at magnetic forces and magnetic fields. Of course, what is a magnetic field? A magnetic field is basically a region where magnetic force can be felt, where magnetic force exists. And most times it's usually indicated by magnetic lines of forces. Now, there are some rules guiding magnetic lines of forces. I'm going to share some with you. First of all, those lines indicate magnetic field. Practically, before I go there, practically, of course, if you want to stop, you've been seeing these fields. These fields are basically hypothetical. They are not real. They are just things we draw. But if you really want to visualize it, you can put some iron fillings. Those grates, just rusted iron. You can break it with your fingers. Those iron powder, those fillings. Put it on a piece of paper. Then keep it on a bar magnet. The filings will arrange themselves in such a way that you can see these few lines here on the right hand side of your screen, right? So that's just by the way. That's just, if you want to actually visualize, you can try that at home. You see it. All right. So please take note. Lines of forces magnetic forces are usually from your north, moves from your north to the south. You can see it in that picture. It moves from your north to the south. Lines of magnetic force do not cross each other. Of course, no lines of force in physics cross each other. Electric force, gravitational force, whatever. None of them cross each other. So please take note of that. And the density, how dense that the lines are indicates the density, how strong the magnet is, right? So stronger magnets will have more dense lines, while weaker magnets will have less dense lines. All right. Please also take note that for conventional magnets, we all know like poles repel, while unlike poles attract. Yeah. So that's basic. That's just basic. Trying to remind you. All right. So let's look at how magnetic field, how magnetic fields behaves around current carrying conductors. So we are going to look at two types of current carrying conductors. We are going to look at a straight conductor, like a straight rod. We are going to look at a coil, something coily in nature. All right. So the magnetic field around a straight conductor, a straight carrying conductor, are usually concentric. In concentric circles, where the center lies on the wire. You can see it here on that screen. Just concentric, round around the wire, and the direction of the field lines can be determined using the right hand thumb rule. So let me just pause and let's go to the right hand thumb rule. How does it work? Here, imagine grabbing a coil with your right hand. Now your four fingers represent the direction of current flow. Please take note, we've done current electricity. It's very different from your electron flow. Direction of current flow is those are your four fingers. While the thumb will definitely point in the direction of what? The magnetic field. The direction of the magnetic field. You can see it is what? It is perpendicular. It is perpendicular. Alright, so we have another type of current carrying a conductor, which is the coil. In this case, the magnetic field lines, right, are straight. They are straight. At the center of the circular loop, the magnetic field lines are straight. Each segment of the circular loop carrying a current produces magnetic field lines in the same direction within the loop. As you can see, I think here we denoted 4 lines there. Taking note, all of them are in the same direction. Of course, you can see it there in the direction there, the arrow is shown there. Now, the direction of the magnetic field at the center of the circular coil is perpendicular to the plane of the coil. Please, this magnetic field is related to the current. Remember, we are looking at current carrying conductor. Magnetic field strength is related to the current by the relation shown here. B is directly proportional to I. You can also put it as B is directly proportional to 1 over R, where R there stands for the radius of the conductor, right? The radius of the conductor. Alright, now finally, we just look at the 8th magnetic field. Of course, it's not just artificial magnets. The 8th also have magnetic properties. The 8th also have magnetic. As a matter of fact, the 8th also has a North Pole, where you have Canada and all that, and the South Pole. I think you have Himalayas around that side. Alright, so how do I know where the South Pole, the 8th South Pole, and the 8th North Pole is? Very simple. I simply pick a conventional magnet, and then I wrap it around a thread, wrap it around a thread, right? And then allow it to hang freely. It's going to oscillate and rest with the North Pole, right? Aligning towards the 8th natural North Pole, while the South will align to the 8th natural South Pole. Please don't think that automatically your up is your North Pole, or probably your North is your North Pole. It's not true. So if you really want to know where the North Pole is and where the South Pole is, the best way to do that is by using your conventional magnet as I have explained. Alright, so what have we done today? We've looked at magnets, we've looked at the type of magnets, we've looked at natural and artificial magnets, right? We've looked at how we can create electromagnets. We've looked at how we can create magnets, different ways we can create magnets, and the different the polarities, how we can control the polarities. We looked at the different ways we can demagnetize a magnet, and we also looked at how how a current carrying rod, how it relates with the magnetic field. Remember we looked at the right hand rule. Yes, we looked at the right hand rule, and we looked at how the magnetic field affects our everyday lives. All right, so we'll see you the next